In the last lesson, I assigned for you to work on magnesium, aluminium, chlorine, and oxygen. To start this lesson off, let's look at the answer for magnesium. Magnesium would have 12 electrons to fill in, and using the simple electron configuration, we'd recall it would be 2, 8, 2. And we'd fill those electrons in by putting 2 on this first level here, like so. That's your 1s2. Then another 2 here. That's your 2s2. And then we'll put in 6 here, like this. 1, 1, 1. Then we'll double that up to make it 8. That's your 2p. And then we go to the 3s. Fill in 1 like this, and then 1 of opposite spins. So therefore, we'll get 282, following all of the rules, starting from the lowest energy level first, ensuring that we fill up a box with electrons of opposite spins, and then move to the next level, and keep going like that. 3 rules: the Pauli exclusion principle, Hund's rule, and the Aufbau principle. Now I'd like you to consider the meaning of this. Writing the electron configuration of magnesium, not as 1s2, 2s2, 2p6, 3s2, but simply as neon in brackets, the neon core, as we say, plus 3s2, because you realize that all of this here belongs to neon. So whenever you write the electron configuration for something that is in the period below neon, anything that is in that period where you have magnesium, where you have aluminium, where you have silicon, you can write neon core to symbolize all of this. So now I'd like you to stop here again, and I'd like you to write the shorthand or the condensed electron configuration for aluminium and for silicon. Now for the last thing today, I want us to consider something that has more electrons than argon. Argon is 2, 8, 8. And we're quite familiar with things that go beyond argon, like 281 is potassium, and 282 is calcium. But going beyond that to something like vanadium, which you see here. And vanadium, if you notice, has 23 electrons to fill in. And I've filled them in, as you see there on the screen, in a slightly different way. Here you can see that the 1s is filled in, and the 2s, and the 2p, and the 3s, and the 3p. And then we get to something a little different. The third shell can hold as many as 18 electrons, and it's made up of 3s, 3p, and 3d. So when we get to levels, when we get to structures like vanadium, then for the first time we have to consider filling in the 3d. But something interesting happens, and that's the 3d actually ends up with more energy than the 4s. And since we have to arrange the electrons in order of lowest energy to highest, we have to find ourselves filling in the 4s box first when we're filling electrons in, and then start with the 3d. And here again, we'll fill up the 4s for vanadium, and there'll be 3 electrons left, and they'll have to go 1 into each box with the same spin, following the rules. So that would be for vanadium. These rules sometimes get slightly broken when we have chromium, and copper, but we'll discuss that in another lesson. For now, I would like you to note that the 3D level has 5 boxes, which means it can hold up to 10 electrons. But in filling up electrons, we need to fill the forest first before we move to the 3D. So I'd like you to write the electron configuration now of manganese and nickel and scandium using the template that I've given you before. Then I'd like you to try to write these electron configurations using the condensed notation. So you're going to draw it with the boxes, then you should write it out like 1s2, 2s2, 2p, etc. And then you'll put some noble gas configuration in brackets and then write the remainder for the condensed configuration. So it's 3 things we need to practice: writing in with the boxes, writing in the full configuration, and finally writing the condensed configuration. Please send your answers to these questions on your Google chat.